All right, let's get you ready for that backflow prevention certification exam. We're going to hit the key terms and concepts that you absolutely need to know to walk in there with confidence and pass. Okay, so here's our game plan. We'll start with the core problem, what is backflow? Then we'll get into the devices that stop it. After that, a quick look at the physics of pressure, the why behind the test. We'll walk through what a test looks like, and then wrap it all up with a rapid-fire review of the terms you've got to know. First things first, let's make sure we're all on the same page about the fundamental problem here. Honestly, if you get this concept down, everything else you'll see on your exam just clicks into place. Okay, here's a term that is guaranteed to be on your test: cross-connection. So what exactly is it, and why is it such a big deal? It's really any physical link, and I mean any link, whether it was put there on purpose or by accident, between our clean, potable drinking water and something that's, well, not. A classic example you'll hear about is a boiler in a building. It's got chemicals in it to prevent rust, and it's hooked up to the water supply to get filled. That connection? That's a cross-connection. So when water decides to flow the wrong way through that cross-connection we just talked about, that's backflow. It's when those nasty boiler chemicals get pulled or pushed back into the pipes that lead to the drinking fountain. This is the exact hazard we're trying to prevent. Now, backflow happens for two main reasons, and you've got to know the difference. First, there's backsiphonage. The easiest way to think about this is like sipping a drink through a straw. A drop in pressure in the water main creates a vacuum, and it literally siphons contaminants back into the system. The other cause is back pressure. This is the opposite. This is when the system on the other side, like that boiler heating up, builds up more pressure than the city water supply and physically pushes its yucky water backward. So, pretty serious problem, right? How in the world do we stop it? Well, that's where our backflow prevention devices come in. They are our first and most important line of defense. Now, for your test, this is a biggie. You have to know that these devices fall into two main camps. On one side, you have your testable assemblies, the RPZ, the double check. These are the mechanical beasts you'll be dealing with out in the field. And on the other side, you have non-testable devices, like the incredibly simple but effective air gap. Let's peek inside two of the most common testable devices. Up top, you see the double check. It's pretty straightforward, right? Two check valves in a row. But look at the one on the bottom, the reduced pressure zone, or RPZ. It also has two check valves, but see that extra piece in the middle? That's a differential pressure relief valve. That little valve is a game changer. It provides an extra layer of safety, which is why you see RPZs protecting against high-hazard situations. Okay, to really understand how we test these things, we have to geek out just for a minute on the basic physics of pressure. I promise, pay attention to these next few concepts because they're the why behind every single step you'll take with your test kit. Everything, and I mean everything, starts with atmospheric pressure. It's just the weight of the air all around us, constantly pushing down. At sea level, that's about 14.7 pounds per square inch. It's our starting point, our baseline for everything else. Now, that fancy gauge in your test kit, it measures what we call gauge pressure, or PSIG. And here's the key thing to remember. When your gauge reads 0, it doesn't mean there's no pressure. It just means the pressure inside the pipe is exactly the same as the atmospheric pressure outside of it. Which brings us to the most important point of all. Your test kit isn't just a pressure gauge. It's a differential pressure gauge. All that means is it's comparing the pressure between two different spots, like before a check valve and after a check valve. That difference is what tells us if the device is actually working. And this slide right here shows you exactly why that pressure difference is so critical. There's a concept called Bernoulli's principle. It sounds complicated, but it's not. It just says that when water moves faster, its pressure drops. This is what causes backsiphonage. Imagine a firefighter opens a hydrant down the street. Water starts rushing through the main. Its pressure plummets, and suddenly you've got a vacuum in the system ready to suck stuff in. Okay, enough with the theory, let's get practical. We're going to walk through a really simplified version of what you'll actually be doing out in the field when you test one of these assemblies. So here's a super basic rundown for testing the first check valve on a double check. You'll connect your high-pressure hose upstream of the valve on test cock 2. Then you connect the low-pressure hose downstream on test cock 3. You bleed out all the air, and then you check the reading on your gauge. The whole point is to trap pressure against that little valve and see if it can hold. And what's the magic number you're looking for? Burn this into your brain for the test. The check valve has to hold at least 1 pound per square inch of differential pressure, 1 PSID. If your gauge reads 1 or higher, it passes. If it's anything less than 1, it fails. It is that simple. All right, we're in the home stretch. Let's do a quick-fire review just to make sure these key terms are locked and loaded in your brain for test day. Ready? First up, what's the name for that type of backflow caused by negative pressure or vacuum in the supply line?
You got it. That's backsiphonage. Just think of a straw.
Okay, next one. What is the only form of backflow prevention that's 100% effective and isn't even a mechanical device? That is the air gap. It's just a simple physical separation. You can't get any more foolproof than that. Look, we've covered the core concepts for your test. You know what backflow is, you know the devices that stop it, and you know the physics behind how we test them. The final step for your exam and for your career is putting all those pieces together. It's about looking at a situation and knowing which device is the right tool for the job to protect public health. You've got this. Good luck.